We are continuing our work on going from one combinational component to another. Okay, and we did a decoder, we did a multiplexer, then we used multiplexer for implementation of random logic, then we did a parity generator or parity checker, the same exact thing, just a bunch of XORs. And now let's go into a very important one, and that is comparator. Comparator is important from 2 points of view. One point of view is that it is a very useful functional unit. Okay, it happens very often that you're counting something. You want to see if you have reached that certain count, or you are greater than something, or two numbers, one is larger than the other one, or you want to see if some number is less than the other, and based on that, make certain decisions in RTL. This happens very, very often. Okay, that's an important functional issue. The other issue is I'm going to be showing you a kind of design that we haven't seen before, and that is iterative design. Okay. In a way, it's like what we have seen before, which is we take a multiplexer and then we cascade it and make it bigger. But then designing something from scratch based on the fact that you are not designing the entire thing and you are only designing one little part of it or one slice of it is what I'm referring to as iterative design, repetitive design. And we'll be seeing that. Okay, so let's get started with the multiplexer and with the comparator, and this is what I'm beginning on. This is a comparator part, and then after that we get into adder, which is again more complex. We have seen a little bit of adder. Remember when I showed you the three variable maps that we were turning them into multiplexers. Actually, those were slice of an adder, which we will see. Just giving you information, so when we get to the adder, you know what it is. And then here, comparator is also, we are showing the slice. What I want to build first is a simple comparator that only has an equal output. Now, the number of bits of A and B, what are they? Let's say A is 8-bit, B is 8-bit, and obviously equal is 1 bit. That becomes 1 when A and B are equal. Okay? How do I do this? Okay, this is a 16-bit input circuit, and then 1-bit output. So do I generate a comparator or a Carnot map with 16 variables and one output? The one output is good, but then 16 variable Carnot map, that's completely impossible. How do we go about this? Look, if I give you two numbers, two decimal numbers, and ask you if to compare them, if the numbers are large, what you do is you start from the left-hand side and decide that, okay, if let's do an example: 38, 29, 28, 36. You start from the left-hand side, and then you say, well, this is greater, so that's why you just don't even look at the other numbers, and then you decide that then A is greater than B. But if you had something like this, 28, 29, and then 28, 38, you would look at this, you say, well, 2 and 2 don't tell me anything, so let's go on and look at the next digit. 8 and 8, again, they don't tell me anything. And then as soon as you get to this one, then you say that B is greater than A. Okay, because you see a 3 and you see a 2. And if you continue seeing equals like this, You start from the left-hand side and you say, well, 2 and 2 are equal, so I haven't made a decision. They're equal so far. Your decision coming into it is that they are equal. And then you go to the right-hand side and eventually you decide whether these are equal or A is greater than B or something. So what you really do is you don't look at all the digits at the same time. You have an algorithm made for yourself that you go through the digits for doing the comparisons. This is decimal. Let's look at bits. Remember this important little circuit, little a, little b, and this is equal 0, 0, 0, 1, 1, 0, 1, 1. If a and b are equal, this becomes 1. What is this? This is an XNOR circuit. A, B, E equal becomes 1 when the two inputs are 0, 0 or 1, 1. Okay, that's why it's XNOR. It turns out the good thing about XNOR is that if you complement A or complement B, not that I'm going to use this, but I'm just giving you some XNOR information. These three circuits are exactly equal. So if you complement A or you complement B or you complement the output, the circuits are the same. Okay? What is this circuit? An XNOR is a 1-bit comparator. Okay? Which becomes 1 when A and B are equal. Okay, fine. Let's say A and B are A 7 colon 0, B 7 colon 0. And I want to compare these. Okay, what I do is, if I look at the whole picture, I say, well, if A 7, B 7 are equal, and A6, B6 are equal, eventually, if A0, B0 are equal, all of these become 1. And then, if they are all equal, then this is A equal B. Or this is my capital 1-bit E output. What if I remove these bubbles from the output of the XORs and make them XNORs and then move them to these inputs? This becomes an OR gate. Okay, so one way of building an equal comparator is to have XNORs for as many bits as you have, and then put a big NOR gate in front. 1, 2, 3, 4, 5, maybe 16, and that gives you your let's say A15, B15, and A0 if this is a 16-bit number you're dealing with, and B0. Okay, and this gives you the equal. This is fine. Okay, it serves the purpose. But then in a way what I'm looking at is I'm looking at all the numbers. Okay, and then if they're all equal, I say, well, it's equal. I'm not doing bit by bit comparing. Okay? I'm not doing what I said I would do, which is looking at this from an iterative point of view. I want to do this now. Again, let's say A7. A is 7 colon 0, B 7 colon 0. Okay? The way I look at it is this. Initially, see when you have two numbers, I'm gonna do binary here. One, two, three, four, 5, 6, 7, 8. Let's keep it this. And okay. You have two binary numbers. And you start from the left-hand side. This is the algorithm I'm presenting, and then I show you the hardware for it. I'm starting from the left-hand side. Just coming in, I assume that since I haven't seen anything to tell me that A is not equal to B. So I assume A is equal to B. And therefore I say, so far, not even reaching this point. Let me show it with a different color. So far, before reaching this point, I am assuming that A and B are equal. And therefore, carrying into this is A is equal to B. Okay? EQ. Then I say, if A7 and B7 are equal, here I have to use XNOR because XNOR tells me equal. And so far coming into this bit, bits have been equal. Then I decide that I am sending equal information to the next bit. That means this. What I'm really doing, if you go back to my original circuit without moving the bubbles, I'm taking this AND gate that I had over here, this AND gate that I had over here, and I'm splitting it into 8 AND gates, each of them connected to the output of one XOR. So what I'm really doing is XNOR. What I'm really doing is this. And equal, XNOR, and equal. And then eventually the last one will give me the equal output. Maybe along the way, one of the bits is two of the bits are not equal. Let's say, for example, A4 are not A4 and B4 are not equal, and then that creates a 0. But then 0 into the AND gate just zeros everything. So at the end, I see no equal. All right. So this is the slice I have. What happens to my slice number 6 is this. A6, B6, and then this one says, well, I'm deciding that A and B are maybe equal, maybe not, but then the decision is not only me, if so far all the bits prior to bit 6 have been equal, then I also announce that they are equal. What does bit 5 say? Bit 5 says exactly the same thing. A5, B5, B5, and A5 are also compared, and they take the AND from the previous one and they just carry it over. by the time I reach A0, B0, okay, I compare those, and then I finally produce my equal output, which is in this case lowercase eq. Let me do this, uppercase eq, which is the output. So what I have built is a comparator with an EQ input, with an EQ output, with 8-bit A, 8-bit B, and this is an equal comparator. The equal becomes 1 if A and B are equal. And then I have an equal input and equal output. And if I were to cascade these, A 15 colon 8, B 15 colon 8, A 7 colon 0, B 7 colon 0. Okay. The upper one becomes my most significant. The lower one becomes my least significant. This becomes my equal output. And then the leftmost equal, I just put a 1 here. Remember what I said? I said that when you I said that when you just come into this from the left hand side, you assume A and B are equal, and therefore you put a 1 there, and then just connect the output equal to the input equal of the next one. So what I have is a cascadable iterative comparator. You just take 8 of these put together, 15 of these put together, 16 of these put together, whatever number you want, and then this works. And then what really happens is if, for example, A7 and B7 are equal, A6 and B6 are equal, A5 and B5 are not equal, then what happens? You bring in a 1 here, you bring in a 1 here. Let me show you with a more brighter color so you can see that easily. So you have a 1 here, A and B are equal, like the example I'm doing, which is 1, 1. A6 and B6 are equal. And let's say at this point, this is 1, 0. And then A5 and B5, A5 is 1, B5 is 0. So you come in with 1 into the upper bit. Then you get a 1 into the bit number 6. A 1 there gives you a 1 into bit number 5. Bit number 5 ignores the 0 and 1 on its input. That's on its inputs. That's 0. 0 and 1 become 0. And therefore, from this point on, all the ands, regardless of what A and B's are saying, all the ands are just sending 0 through, and therefore you get the 0 on the output. All right, that's a cascadable, iterative, 1-bit comparator only gives you an equal output. I'm going to extend this now to a comparator that does equal and greater than. Okay, once again, I start with coming in assuming that A and B are equal so far. Coming in. I also assume that I haven't decided that A is greater than B. Then I put bit number I of A on one input, bit number I of B on another input. Now, the logic that I showed you for equal remains the same. Okay, but now let's look at the logic for the greater part. I'm going to put an example here and play with this example. This is my A, this is my B. 1 1 0 0 1 0 0 1. B is 1 1 0 0 0 1 1 0. Okay? When I come in, A and B are equal. Okay? And therefore, the equal input is 1. Then AI and BI decide that, okay, if so far things have been equal, then A and B decide that the equal out is going to be 1 or not. Okay? That's with the equal which we have already seen. But then, if this slice decides that if this is slice, what comes into this is that GT from the previous bits is 1. GT from the previous bits is 1. What it means is that, first of all, I know that equal is not going to be 1, but then GT from the previous bits has been 1. That means, for example, A was 1 0 1 0. B was, let's say, 0 1 0. By the time you reach bit number, the second bit from the left, the decision has already been made that A is greater than B. A is greater than B. So what do you say? Well, you say, well, since the decision has been made by upper level bits, who am I to decide if lower bits decide with? Okay, let's do it this way. If the decision has already been made by upper level bits, lower level bits are in no position to override that decision. Okay? Like, for example, if you have 395, you have 266. If the decision has already been made by 3 that A is greater than B, then the rest of the digits are in no position to override that. Okay? And therefore I say, well, if the decision has already been made, just pass on the decision to the next bit because the decision has already been made, and let that other bit also pass on the same information. Okay? So that's the reason for this OR. When would you make a decision? You would make a decision only if you get to a certain digit, and you find that, for example, so far all the digits have been equal. Okay? In this binary example, here A and B are equal, so you are making no decision. You're just saying, well, equal passes. Passes on to the next one. The next one, the same thing. The next one, the same thing. The next one, the same thing. Then you get to this bit here. When you get to that bit, you say, so far the decision has been A is equal to B. Okay? Then you say, if so far A is equal to B, then this particular bit is in a position to make a decision. And therefore you say, if so far, that means the equal input is 1, and if A is greater than B, for binary, A is greater than B is only A is 1, B is 0, right? And therefore you put a 1, 0 here. If in this bit you decide that the previous bits have all been equal, and you are deciding that your A is greater than B, then you decide that, okay, now I can make a decision that A is greater than B and feed it to the next input or the other input of the OR gate, deciding who is greater. And therefore this continues on and on and on. So what I had over here was a comparator that only checks equal. This comparator not only checks equal, it also checks greater. Now you want to have a larger comparator, an 8-bit comparator. Just take this slice, this iterative slice, and then wire it from the left to the right. And this is what I have over here. See, what happens is for a 4-bit, the diagram is good enough for that. A3, B3, and then my initial input equal is 1. GT is 0. That means I have decided before even reaching A3 and B3, I've decided that A and B are equal, not coming in, and I've decided that I haven't decided that A is greater than B. Therefore, you put a 0 there. Okay, that's the leftmost. And then from that point on, you connect the EQ to the EQ of the next slice, the GT output to the GT input of the next slice, and go on and on and on until you get to the rightmost bit. The rightmost bit, whatever it says, is the collective information from all previous bits. Okay? And therefore I have 1 slice, 2 slices, 16 slices, A 15, B 15 equal GT. This is 1, this is 0, and then finally this is GT, this is EQ. Okay? And then this is A0, B0. That's an iterative comparator. And let's go back here. How do you write the Verilog description of it? Well, the Verilog description of this is GT is GT, or I'm just writing this gate level circuit right up here. GT is GT or EQ. Okay, EQ ended with A, ended with B bar, which is this these two AND gates feeding the left input of the OR gate. And how about the equal? Equal is if the input equal is 1, and then if A is 0, if A and B XNOR of it. Remember I said that XNOR, you can complement either A or B or the output. So this is equal ended with XNOR of A and B. That gives you the equal output. What's wrong with this comparator? What is wrong with this comparator is for you to get the result, you have to wait for each slice to go through. And then look at the longest path here. The equal path is 5 nanoseconds, but then the GT path is from equal input to the GT output, that's 10 nanoseconds. What it means is if you have a 16-bit comparator, you have to wait 100. That's the worst case scenario. You have to wait 160 nanoseconds for the output to become ready. Nevertheless, this is describing one of these slices, and then you can just repeat these slices. Alternatively, instead of doing this, you can just write down an assign statement to compare A and B. So let me do this. You can always write something like this. Assign EQ equal, that's the equal output, EQ equal, if A is equal to B, then 1 tick B 1, otherwise 1 tick B 0. assign gt equal, if a is greater than b, then 1 tick b 1, otherwise 1 tick b 0. Okay, something else you can do. You can say, instead of that, you can do that, but maybe you want it to be more explicit and you can read it better. You can also do this. EQ assign EQ equal A equal B. That's it. Assign GT equal A greater than B. That works too. Okay? Also, the circuit works too. Write down those two assign statements and then repeat the assign statements as many times as you like. That's one way of doing comparing. Another comparator which works slightly different, not slightly. We started with the most significant bit in the previous comparator and then go to the right hand side. And the result comes out of the right hand side. What is happening here? The left hand side makes a decision and then propagates the decision to the right hand side. You eventually get your result from this right hand side. Instead of doing this, we can also do this. We can say, well, let the left hand side, if it can make the decision, announce the decision itself. Okay, so if this bit can make a decision that A is greater than B, let it announce it. And only go look at the bit next to it if that bit, that leftmost bit, cannot make a decision. Okay? So this is how I'm going to do this. I build a comparator, let's say a 4-bit comparator. With L less than, G greater than, E equal inputs, and LT, EQ, GT outputs. I have same inputs as outputs. This comparator says this. If A is greater than B, I'm going to announce it right there. Okay? So this becomes my graded output. If A is less than B, I'm going to announce it right there. This comparator, this 4-bit comparator, says, if I cannot make a decision, that means if A and B are equal, what I do is, whatever the right bit is telling me, I'm going to take those and put them on these 3 outputs. That means these are equal. I cannot make a decision. Let's see what the person to my right is saying, and then take that information and announce it through my own outputs. Okay, so in decimal it becomes something like this. You have this number here, 87, 59, 87, 30, 8. Okay? You are getting your output from here. These two are compared, and we say that we are not making a decision because these two are equal. Let's ask the guy to my right. And therefore, these two say, let's see what these people are saying, and let's take that information and put it on the output. Then I go to the guy on the right hand side. What are those people saying? Those people are saying 7 and 7, those are also equal. They say, well, even though I passed my information on to the guy to my left, but I'm not the one who is making the decision. Actually, because these are equal, I am making the decision based on what the guys to my right is saying. Okay? And then I reach the guys to the right, the 5 and 3. 5 and 3 are going to say that A is greater than B. And therefore, via the blue lines, A greater than B is going to be announced. And since the two digits to the left, we're not making any decision, that A greater than B will be outputted from the very leftmost bit or very leftmost bit 4-bit comparator. Okay, these are hardware components. It doesn't mean that these four that are making these decisions, once a decision is made by the third digits from the left hand side, it doesn't mean that the digit to the right is not making a decision. The digit to the right also, this one is also making a decision. See, these two are also making a decision. These two are saying B is greater than A. But nobody listens to it. Nobody listens to it because listening stops when the digits to the left are no longer equal. So this one, if you look at its own output, it's saying B is equal to B is greater than A. Okay? But then the blue slice is saying, well, look, I've already made a decision, and those guys to my left have already taken that decision, announced it through the output. So we are ignoring what you're saying. When do you listen to the guy to the left, to the right? When do you listen to the guy to the right? All the way to the right. 8, 7, 5, 6, 8, 7, 5, 6. This one says I cannot make the decision as the guy to my right. This one says, okay, I pass on the information to you. Here. This guy says I pass on the information to you. Whatever is passed on to you, you announce it to whoever is your customer. Then digit 7 is going to say these are equal, so I'm not making a decision. I'm just depending on whoever is on the right hand side and asking that person. And then that information comes in here to the 7. The 7 passes it along to the 8s. The 5s look at the inputs. They say, well, we are not making a decision either. So what we have to do is to ask the guy to the right. The 6, they say, we are not making a decision either. Okay? Because the two digits are the same. And therefore, I'm going to pass my input information to the left. To the left, to the left. Finally, it comes out of the left-hand side. What information do I put on the rightmost digits? I put a 0 here, a 1 here, a 0 here. I'm sorry, this is, okay. Yeah, this should be equal here, G here. Okay. So I put in a 0 here, a 1 here, a 0 here. So if all digits are the same, this is the rightmost digit. If all digits are the same, this 0, 1, 0 will go, go, go. And then finally, you get 0, 1, 0 on the three outputs, L, LT, EQ, and GT. So the way it works is exactly listen to what I said before. If A is greater than B, this 4-bit comparator decides that GT is 1. Nobody overwrites that GT is 1. If A is less than B, this 4-bit says, well, I've decided that these 4 bits are deciding that A is less than B, so I announce that a LT is 1. Okay? You only listen to the guy next to you. See, this is GT is 1. This is LT is 1. You only listen to the guy to your right if A and B are equal. If A and B are equal, this digit is saying, I'm not making the decision. I take whatever is on my L input, E input, G input, and pass on to the LT output, EQ output, and the GT output. Okay? What's the Verilog description? I'll show you the circuit in a second. You have two 4-bit A and B. You have the less than, equal, and greater, less than, equal, and greater inputs and outputs. Okay? My 3 outputs of 1 unit, of this 1 unit, this less than, equal, greater, 4-bit A, 4-bit B, and then you have LT, EQ, GT. I put these in curly brackets, so I make it a 3-bit vector. The 3-bit vector is if A is less than B, okay, since LT is on the left, I put 3 tick B 1 0 0. Okay, what it means is LT becomes 1. If A is greater than B, 3 tick B 0 0 1, that means GT becomes 1. Okay. Use the power of colors. This is this. And then this. Sorry. This is this. The decision is made in these two cases. If A is equal to B, then you say, let's concatenate L and E and G. That becomes a 3-bit vector. Curly bracket means concatenate. These single bits, that becomes a 3-bit vector, and the 3-bit vector goes into L, EQ, GT. That means that's the situation that no decision is made. Whatever is on the input L goes on the output L. Whatever is on the input E goes on the output EQ. Whatever is on the input G goes on the output GT. Okay? If you want to make this a bigger comparator, you have 2 ways of doing it. One would be just change this to 15. That's all there is to it. No, you also have to change these numbers. If this is 15, you want to have a... no, you don't have to change these numbers. Sorry. If this is 15, all 16-bit comparator, that's all you have to do. But if you go and look in your bag of comparators, you only have 4-bit comparators, but then you want to build a larger comparator, this is how you do it. Okay, you take A15 colon 0, B15 colon 0. Take the uppermost 4 bits, give it to the most significant comparator. Take bits 11 to 8 for the next one, 7 to 4 for the next one, and for the rightmost bit, the one whose decision is ignored if the upper ones have already made the decision, take the bits 3 colon 0 and give it to that, and then if that one cannot make a decision, you are putting 0 1 0 on the L, E, G inputs, and this 0 1 0 is the one that will be passing through. So in case if So actually the flow goes like this. See, the flow goes like this. This decision goes here, this decision goes here, this decision goes here, and this decision will be announced through the outputs coming from the left-hand side. And if you decided that you want to have a comparator with the output A instead of GT, you want GT or equal, all you do is you put a 1 here. Instead of having 0, 1, 0, you put 0, 1, 1. That means if they're equal, okay, this output is also going to be 1, and therefore this becomes GT or EQ. Okay. One simple application of comparators, a maximum circuit finder. This is a comparator. You don't really have to have a cascadable comparator like this. A simple comparator that would only give you the GT, that was the first one, would do the job. If A is greater than B, this becomes 1. In that case, you want A to go to the output. Okay? So because if it becomes 1, then the lower input is taken. The lower input is now connected to A, and therefore the A input is going to go to the output. That's a simple application. I'm going to show you something else before I leave. If you have a 16-bit comparator or 4-bit comparator, whatever size comparator you have. Okay. These are all magnitude comparator. 1, 2, 3, 4, let's say. 3, 2, 1, 0. 3, 2, 1, 0. And let's say we are talking about this last comparator here. This is less than, equal, greater than. This is less than, equal, greater than. Okay? Let's talk about 4-bit numbers. These 4-bit numbers, if it is 1, 0, 0, 1, 0, 1, 1, 0, okay, this comparator works. What if these are 2's complement numbers? See, if these are 2's complement numbers, for as long as the numbers have the same sign, there's still the comparator is still good. Okay, look at this. See, this is 0, 1, 1, 0. That's 6, and this is 0, 1, 0, 1, that's 5. You give it to this comparator, it's going to say that A is greater than B. That's if 2's complement. So this is 6, this is 5. This is minus 6. This is minus 5. Okay. This is a magnitude comparator. You know the numbers are negative, but this one is saying 2 numbers, and then it's going to say 1, 0, 1, 1. It's looking at it as 11, and therefore it's saying this is larger, and it is correct. So for as long as the 2 numbers have the same sign, it's correct. If the numbers have different signs, that's where this magnitude comparator goes wrong. Different sign means that A is 0, 1, 1, 0. B is 1, 0, 1, 1. This is 6. This is minus 5 for you. The comparator sees this as 11 and sees this as 6, so he's going to say B is bigger. You don't like that answer. So what you're going to do is You want to say the comparator still works the same way for as long as sign bits are equal if I just complement the the leftmost bit. Okay? So these become your inputs. If you still have the same sign, it doesn't matter. You're complementing, and instead of A0110, you are giving to the comparator 1110, and for B, you are giving it 1101. 1110 is still larger than B. The comparator is going to say, yes, is larger. It doesn't know that it has been fooled. Okay, so for as long as the sign bits are the same, this comparator works. If you complement. What if you have this case over here that the comparator was not working? Now what you are doing, you are fooling it and giving 1110 to the A input and giving 0100 to the B input. No, I'm sorry. You are giving, only the leftmost bit changes. The comparator is going to look at this. It says, what? A 14. Looks at this. It sees 3. It says A is larger. Bingo. You fooled it into thinking that these are magnitudes, and then you are getting the right result out of this. Okay, so if you have a comparator, it's a magnitude comparator. You want to make a signed number 2's complement comparator. Just invert the most significant bits or the sign bits. All right, we are done with comparator.